Hello everybody, it's Mr. Woodward here. In this video, I'm going to talk about two types of mechanical energy. Let's take a look here at the top. Energy is the ability to do work, and it comes in many forms: electrical energy, chemical energy, thermal energy. But here we will focus on just mechanical energy. Okay, and so mechanical energy has two basic types. Number one is kinetic energy. Number two is potential energy. So let's focus on kinetic energy for a moment. Kinetic energy is the energy of motion. Something's got to be moving if it has kinetic energy. Objects that are moving have kinetic energy that is related to their mass and how fast they are moving. And so here is the kinetic energy equation that will be used so often that it would even be helpful for you to memorize it. But it's 1/2 mv squared. Okay, m is for mass. That's going to be in kilograms, and v is for velocity, which will be in meters per second. And that will end up giving you a kinetic energy in a unit called joules. I'll come back to that in a moment. Kinetic energy measured in joules. Okay, so kinetic energy is the energy of motion. It's dependent on its mass and the speed or velocity of an object. That will give you its kinetic energy. But there's this other type of mechanical energy called potential energy. Potential energy is energy that is stored. So I'm just going to focus on one type of potential energy in this video. There's gravitational potential energy, and there's another type of potential energy called spring or elastic potential energy. I'm just going to focus on gravitational potential energy here. And specifically, gravitational potential energy is stored in a gravitational field. And it's related to the strength of the field, the mass of an object, and the object's position within that field. Specifically, its height above the ground if we're talking about like Earth's gravitational field or something like that. Okay, so gravitational potential energy is mgh. We've got mass times gravity times height. And I'm just going to label these. M for mass. Again, that's in kilograms. And g is for the acceleration due to gravity. And that's, for the Earth, that's 9.8 meters per second squared. So we're going to be using that mostly for lowercase g. And then h is the height above some arbitrarily assigned zero height point. So height above, I'll say quote unquote, 0. Okay, you get to decide where 0 is, but that height is going to be measured in meters. Okay, so m times g times h, mass times the acceleration due to gravity times the height within that field, and you get to define where the 0 height mark is. So here's an example of a roller coaster ride, right? If you start at rest at the top, so if you start here and then you roll down, your kinetic energy and your gravitational potential energy might look something like this. So starting at the beginning here, we've got no kinetic energy and 100% potential energy. And that would be based on some arbitrarily assigned 0 height level, which usually is put right at the bottom. And so I would maybe draw this line here. I'm going to say, yep, at that point, the height is 0. Okay, so with reference to there would be no kinetic energy because you're starting at rest. So I'm going to say V initial is 0 here. So that explains why the kinetic energy is 0. And then the potential energy is going to be like 100%. And then as you roll down this roller coaster, your energy types begin to change. So then halfway down, now you are 50% of both. And then as you reach the bottom here, now you're 100% kinetic energy and 0% potential because your height is now 0, right? And if your height is 0, you have no gravitational potential energy. So all of your energy must be kinetic energy. And by the way, at this point, down here, you'd be going quite fast at this point. So that's why you have all this kinetic energy. And then as you start to rise up again to the end, you start to gain potential energy because your height increases, and so that, but at the same time you lose speed because you're rising up against gravity, and so your potential energy jumps up, your kinetic energy jumps down. So the two types of energy are always sort of exchanging places, and the values are changing depending on your height above ground and how fast you're going. So I mentioned that I was going to come back to this idea of energy being measured in joules, and so here's my note. Energy is measured in the unit of joules, named after James Joule, and here's a picture of him right here. He was a British physicist whose experiments about energy transformations were first published in 1843. And what is a joule exactly? So I'm going to kind of show you how the unit of joule is related to the familiar units of kilograms, meters, and seconds. So 1 joule is, by definition, 1 Newton times a meter. Okay, a joule is a Newton meter. Well, all right, what is a Newton meter? So a Newton meter is, first of all, a Newton is a kilogram meter per second squared. And then I would multiply that by a meter again, right? So here's my meter there, and here's my Newton. A Newton is a kilogram meter per second squared. And so then I could actually go one step further, and I could say, well, 1 kilogram meter per second squared times a meter would just be 1 kilogram meter squared per second squared. Okay, so this is a joule at its most fundamental units, a kilogram meter squared per second squared. That's kind of a lot to remember. So most people just remember that a joule is a Newton meter. It's usually easier for most people to remember. Okay, but either way, that's how a joule is related to our base units of kilograms, meters, and seconds. All right, in the next video, I'm going to take a look at a couple of examples of how to do some energy calculations related to kinetic and potential.